The oldest thing in the universe is not a star, a galaxy, or a black hole. It is light. Ancient light was released when the cosmos was still young, long before the formation of planets and galaxies. Against all odds, that light has continued its journey across the universe for billions of years. It surrounds us even now, carrying clues about the earliest moments of cosmic history. Scientists have learned to detect this remarkable signal, turning it into one of the most important discoveries in modern astronomy. Tonight, we follow the oldest light in existence and uncover why the ghost of the Big Bang is still traveling through the universe today. When most people think about ancient objects in the universe, they imagine distant galaxies, massive stars, or perhaps ancient black holes that have existed for billions of years. It seems reasonable to assume that the oldest thing in existence would be some incredibly old celestial object still drifting through space. Yet the universe holds a remarkable surprise. The oldest thing we can observe is not a physical object at all. It is light. This light is so ancient that it began its journey long before the first stars existed. It traveled through space before galaxies formed, before planets emerged, and before the universe developed the complex structures we see today. In many ways, it is a messenger from a time when the cosmos was still in its infancy. To understand where this light came from, we must travel back nearly 13.8 billion years to the earliest chapter of cosmic history. The universe began in an incredibly hot and dense state. Temperatures were so extreme that matter as we know it could not exist. Atoms had not yet formed. Stars did not exist. Even light itself faced a challenge. Although enormous amounts of radiation filled the young universe, it could not travel freely. The reason was simple. The early cosmos was packed with charged particles moving at extraordinary speeds. Electrons and atomic nuclei filled every region of space. Whenever a particle of light attempted to move through this environment, it quickly collided with one of these charged particles and changed direction. This happened over and over again. Imagine trying to shine a flashlight through an incredibly dense fog. The light would scatter in every direction, making it impossible to see very far. The early universe behaved in a similar way. It was not dark because there was no light. It was opaque because light could not travel freely. For hundreds of thousands of years, the universe remained trapped in this state. During this period, space continued expanding. As it expanded, temperatures gradually decreased. The cosmos slowly cooled enough for one of the most important transitions in cosmic history to occur. Electrons began combining with atomic nuclei to form the first stable atoms, primarily hydrogen and helium. This change transformed the universe. Suddenly, there were far fewer free charged particles available to scatter light. The dense cosmic fog began to clear. For the first time, light could move freely across vast distances. The photons released during this moment began a journey that continues even today. They traveled through the expanding universe for billions of years, crossing unimaginable distances and surviving every stage of cosmic evolution. While stars were born and died, galaxies collided, and planets formed around distant suns. This ancient light continued moving through space. What makes this light extraordinary is that it has never stopped traveling. It still fills the universe in every direction. Every region of space is immersed in this faint glow from the distant past. Although it has stretched and cooled dramatically as the universe expanded, it remains detectable with sensitive instruments. Scientists call this ancient signal the cosmic microwave background. Often shortened to the CMB, it represents the oldest light that can be observed directly. When astronomers study it, they are not merely looking at distant radiation, they are looking back in time to a period only about 380,000 years after the Big Bang, making it one of the earliest visible records in existence. The cosmic microwave background is the universe's oldest photograph. It preserves a snapshot of the cosmos before stars, galaxies, and planets existed. Every photon within it has been traveling across space for more than 13 billion years, carrying information about conditions that existed near the beginning of cosmic history. This is why the oldest light in existence is so important. It allows scientists to study an era that would otherwise be inaccessible. It serves as a direct connection between the modern universe and its earliest observable chapter. Long before the first stars illuminated the heavens, this ancient light began its endless journey, and even now, billions of years later, it continues passing silently through the cosmos, carrying the memory of a universe that was only just beginning to emerge. When people imagine the early universe, they often picture a vast empty space filled with darkness. In reality, the young cosmos was nothing like the quiet universe we know today. It was an extremely hot, crowded, and chaotic environment where matter and energy were packed together so densely that almost nothing could travel freely. Long before the first stars appeared, and long before galaxies began taking shape, the universe existed in a state that would be completely unrecognizable to us. This was the era before the universe became transparent. To understand what that means, imagine standing inside a thick cloud of smoke. Even if a bright light is shining nearby, you cannot see very far because the smoke constantly scatters the light in different directions. The light exists, but it cannot travel in a straight path long enough to reach your eyes clearly. The early universe behaved in a similar way, except on a cosmic scale. Only moments after the Big Bang, the universe was incredibly hot. Temperatures were so extreme that atoms could not exist. Under ordinary conditions, atoms are formed when negatively charged electrons orbit positively charged nuclei. But in the early cosmos, the heat was so intense that electrons and nuclei could not remain together. Every time they attempted to combine, the surrounding energy immediately tore them apart again. The universe became filled with a dense mixture of free electrons, atomic nuclei, and radiation. Scientists often describe this state as a plasma, a form of matter very different from the solids, liquids, and gases we experience in everyday life. Inside this plasma, light particles called photons were trapped. Whenever a photon tried to travel through space, it quickly collided with a free electron. The collision changed the photon's direction, sending it somewhere else. Moments later, another collision occurred, then another, and another. The process repeated endlessly. Rather than moving freely across the universe, light was constantly scattered in every direction. The cosmos was glowing intensely, yet no photon could travel very far before being interrupted. This creates an interesting paradox. The early universe was filled with enormous amounts of light, but it was effectively opaque. If a hypothetical observer could somehow survive in that environment, they would not see distant objects because light could not cross large distances. The universe was bright, yet visibility was almost non-existent. For hundreds of thousands of years, this condition remained largely unchanged. Something important was happening. The universe was expanding. Since the moment of the Big Bang, space itself has been growing larger. As space expanded, the energy within it became spread over a greater volume. This caused temperatures to gradually decrease. The cooling happened slowly on human scales, but rapidly on cosmic timescales. As the universe cooled, conditions began moving toward a critical turning point. Temperatures dropped enough for electrons and atomic nuclei to combine permanently. Instead of existing separately, they joined together to form the first stable atoms, primarily hydrogen and helium. This event was one of the most important transitions in cosmic history. Before it occurred, free electrons filled the universe and constantly scattered light. After it occurred, most electrons became locked inside atoms. Suddenly, there were far fewer charged particles available to interfere with photons. The cosmic fog that had filled the universe for hundreds of thousands of years began to disappear. Light could travel freely through space. This moment is often called recombination, although the name can be slightly misleading because it was actually the first time stable atoms formed in the young universe. What matters most is what happened next. The universe became transparent. Imagine a dense fog slowly lifting after a storm. As visibility improves, distant landscapes that were previously hidden suddenly become visible. The same thing happened on a cosmic scale. The universe transitioned from an opaque plasma into a transparent cosmos where light could finally begin its uninterrupted journey. The photons released during this transition are the same photons that astronomers detect today as the cosmic microwave background. They are ancient survivors from the moment the universe first became transparent. This is why the era before transparency is so important. It represents a period that can never be observed directly using ordinary light. Any photons that existed before transparency were constantly scattered and lost information about their origins. They cannot provide a clear picture of what happened earlier because their paths were endlessly interrupted. The transparent universe marks the beginning of the oldest visible chapter in cosmic history. Everything that happened before remains hidden behind a wall of plasma, much like events occurring behind a dense fog bank. Scientists can study that earlier era through mathematics, particle physics, and indirect evidence, but they cannot see it directly with light. The moment transparency arrived changed everything. Light that had been trapped for hundreds of thousands of years was suddenly released into the expanding cosmos. Those photons began traveling across space, carrying with them a record of the universe at that exact moment. More than 13 billion years later, they are still moving. Every direction we look in the sky contains traces of that ancient release. The universe may have changed dramatically since then. Stars have formed and died. Galaxies have grown and collided. Planets have emerged around countless suns. Entire cosmic structures have evolved across billions of years. Yet beneath all of those changes remains a faint glow from the time when the universe first became transparent. It is the oldest light humanity can observe, and it marks the moment when the cosmos emerged from its primordial fog and allowed its story to become visible for the first time. For hundreds of thousands of years after the Big Bang, light was trapped. The young universe was filled with a dense plasma of free electrons and atomic nuclei, creating a cosmic fog that prevented photons from traveling freely. Light existed everywhere, yet it could not escape. Every attempt to move across space ended in another collision. The universe was glowing intensely, but that glow remained imprisoned within the dense environment of the early cosmos. Then everything changed. As the universe continued expanding, it steadily cooled. Temperatures that had once been unimaginably high began to fall. Over time, conditions reached a critical threshold where electrons could finally combine with atomic nuclei and remain together. For the first time, stable hydrogen and helium atoms began forming throughout the universe. This might seem like a simple chemical transition. In reality, it was one of the most important events in cosmic history. The formation of atoms transformed the entire nature of the universe. Before this moment, free electrons were everywhere. These charged particles constantly scattered photons, preventing light from traveling any significant distance. Once electrons became bound inside atoms, most of those obstacles disappeared. Suddenly, the universe became transparent. The effect was dramatic. Imagine a vast fog covering an entire landscape for centuries. Then, almost everywhere at once, the fog begins to vanish. Mountains, valleys, and distant horizons become visible for the first time. The universe experienced a similar transformation. The cosmic fog that had trapped light for hundreds of thousands of years finally cleared. The photons that had been endlessly bouncing between particles were suddenly free to move. This event is sometimes called the release of first light. Although it was not the creation of light itself, light had existed long before. What changed was its freedom. Photons that had once been trapped inside the dense plasma could now travel uninterrupted across enormous distances. The universe opened its eyes. For the first time, information carried by light could move through space without constantly losing its direction. This marked the beginning of the oldest observable signal in existence. What makes this event so extraordinary is that it happened everywhere at nearly the same time. There was no single location where the release occurred. The entire observable universe underwent the transition together. Across billions of light years, photons began their long journey through the cosmos. Those photons did not know what the future held. They began traveling long before the first stars ignited. They crossed space before galaxies assembled into their modern forms. They continued moving while black holes formed, while planetary systems emerged, and while life eventually appeared on at least one small world orbiting an ordinary star. The universe changed dramatically around them, yet they kept going. As the cosmos expanded, these ancient photons experienced another remarkable effect. The stretching of space itself gradually stretched the wavelengths of the light traveling through it. What began as visible and infrared radiation slowly shifted into longer wavelengths. Over billions of years, the light cooled and transformed into microwave radiation. This is why the ancient glow of the Big Bang is no longer visible to human eyes. If our eyes were sensitive to microwave wavelengths, the entire sky would appear filled with a faint and nearly uniform glow. Instead, specialized instruments are required to detect it. Hidden beyond ordinary vision, the oldest light in the universe still surrounds us today. The release of this light was not simply an important event, it was the moment that created a permanent record of the early universe. Every photon carried information about the conditions that existed when it last interacted with matter. Temperature, density, and tiny variations in the young cosmos became encoded within the radiation itself. These photons effectively became cosmic messengers. For more than 13 billion years, they have carried a snapshot of the infant universe across space and time. By detecting and studying them, scientists can reconstruct conditions that existed long before any stars or galaxies had formed. Few events in cosmic history have had such lasting consequences. The birth of stars changed the appearance of the universe. The formation of galaxies created large-scale structure. The emergence of planets produced countless new worlds. Yet all of these developments came later. The great release of light occurred first. It marked the moment when the universe transitioned from an opaque plasma into a transparent cosmos. It allowed ancient photons to begin an uninterrupted journey that continues even now. Every direction we observe in the sky contains traces of that remarkable release. Even after billions of years, the evidence remains. The ancient light has never stopped traveling. It continues crossing the universe today, carrying with it a memory of a time when the cosmos was only a tiny fraction of its current age. In many ways, the Great Release was the universe's first visible message to the future, a message that humanity would not learn how to read until billions of years later. When people hear that the oldest light in the universe was released more than 13 billion years ago, they often assume that its journey must have ended long ago. After all, light travels at an incredible speed. It can circle Earth more than 7 times in a single second. It can travel from the Sun to Earth in about 8 minutes. On everyday scales, light seems almost unstoppable. So why is the first light of the universe still here? Why has it not simply passed by and disappeared into the distant cosmos? The answer lies in one of the strangest and most important features of our universe. Space itself is expanding. Many people imagine the universe as a giant empty container filled with galaxies moving through it. While that picture is useful in some situations, it can also be misleading. According to modern cosmology, galaxies are not simply traveling through static space. The fabric of space itself is stretching. Distances between large regions of the universe gradually increase over time. This expansion changes everything about how light behaves across cosmic distances. Imagine drawing 2 dots on the surface of a balloon. As the balloon inflates, the dots move farther apart, even though neither dot is actively traveling across the surface. The expansion of the surface itself increases the distance between them. The universe behaves in a somewhat similar way. As space expands, light traveling through it experiences a remarkable effect. The wavelength of the light becomes stretched along with space itself. Short wavelengths gradually become longer. High-energy light slowly loses energy as the universe grows larger. This process is known as cosmological redshift. When the first light of the universe was released, it was not microwave radiation. The photons carried far more energy than they do today. Their wavelengths were much shorter because the universe was much smaller. hotter and denser. But as billions of years passed, the expanding cosmos stretched those wavelengths again and again. The light did not disappear. It changed. What was once energetic radiation gradually transformed into lower energy microwave radiation spread across the sky. This stretching is one of the reasons the ancient light remains detectable today. Instead of ending its journey, it adapted to the changing universe around it. There is another reason the first light never reached an end. Unlike a beam from a flashlight, the cosmic microwave background was not emitted from a single source traveling in one direction. The release occurred throughout the entire observable universe almost simultaneously. Every region of space became transparent, allowing photons to begin traveling freely. The ancient light was released in every direction at once. Imagine standing in the middle of a vast forest during a gentle snowfall. Snowflakes are falling from every part of the sky. No matter which direction you look, flakes continue drifting toward you. You are not seeing the same snowflake repeatedly. You are constantly encountering new ones arriving from different locations. The cosmic microwave background works in a similar way. The photons reaching Earth today are not the exact same photons that arrived yesterday or 1,000 years ago. New ancient photons continue arriving from more distant regions of space. Every direction in the sky contains light that began its journey billions of years ago. This creates a fascinating consequence. No matter where astronomers point their instruments, they detect this ancient glow. Look north, and it is there. Look south, and it is there. Look toward distant galaxies or seemingly empty regions of space, and it is still there. The entire universe appears immersed in this faint radiation because the source of the light surrounds us in every direction. We exist inside a vast ocean of ancient photons. Another important factor involves the immense scale of the universe itself. The observable universe spans tens of billions of light years in every direction. Even though light travels incredibly fast, the cosmos is so vast that photons released billions of years ago are still arriving from distant regions. And because the universe continues expanding, new regions become observable over time. Light that once could not reach us may eventually become detectable as cosmic history unfolds. This means the story of the first light is not something that happened and ended long ago. It is something we continue experiencing right now. Every second, ancient photons pass through Earth. They move through the atmosphere. They pass through buildings, oceans, mountains, and even our bodies. Most people never notice because the radiation is extremely faint and exists at microwave wavelength invisible to human eyes. Yet it is everywhere. A small fraction of the static seen on old analog television screens came from the cosmic microwave background. Long before many people understood what they were observing, traces of the oldest light in the universe were already reaching their homes. This remarkable fact reveals something profound about cosmic history. The universe did not simply create this light and then leave it behind. The photons released during the era of recombination became permanent travelers, carrying information across billions of years of cosmic evolution. They witnessed the birth of the first stars. They crossed space as galaxies assembled. They continued traveling while clusters of galaxies formed immense structures stretching across hundreds of millions of light years. They passed through regions where black holes emerged and where planetary systems developed around newborn stars. Throughout all of these events, the ancient light kept moving. It became a silent observer of cosmic history. What makes this even more extraordinary is that the photons themselves barely changed except for the stretching caused by cosmic expansion. They continued carrying information about the conditions that existed when the universe was only about 380,000 years old. In other words, every photon acts like a tiny time capsule. By studying these photons, astronomers can reconstruct a picture of the universe long before stars illuminated the cosmos. The light serves as a direct connection to one of the earliest observable moments in existence. This is why scientists often describe the cosmic microwave background as a relic of the Big Bang, not because it is frozen in time, but because it has survived for billions of years while preserving a record of the distant past. Its journey never truly ended because there was never a final destination. The photons continue moving through the expanding universe, crossing vast distances that stretch even as they travel. They are part of an ongoing cosmic process rather than a completed event. The most beautiful aspect of this story is what it reveals about the universe itself. The cosmos possesses a memory. Events that occurred more than 13 billion years ago have not completely vanished. Their traces remain woven into the fabric of reality, still detectable by those who know how to look. The first light is one of the clearest examples of this cosmic memory. It reminds us that the universe carries records of its own history. Every ancient photon crossing space today is evidence that the earliest chapter of cosmic existence has never entirely faded away. The first light never reached an end because its journey is still unfolding. Even now, as you listen to this story, photons released near the dawn of time continue passing silently through the universe, carrying with them a message from an age before stars, before galaxies, and before anything familiar existed. More than 13 billion years later, that message is still being delivered. As you sit reading these words, you are surrounded by one of the oldest things in existence. It is passing through the room around you, moving through the air, through the walls, and even through your body. You cannot see it, you cannot hear it, you cannot feel it, yet it is present everywhere. This ancient presence is the cosmic microwave background, the faint glow left behind by the early universe. It is the oldest light that can still be observed, and unlike distant stars or remote galaxies, it is not located somewhere far away in the depths of space. It surrounds us continuously. In fact, there is no place within the observable universe where this ancient radiation is absent. Many people imagine space as mostly empty. While space is indeed incredibly sparse compared to conditions on Earth, it is not completely empty. Every region of the cosmos contains traces of the ancient radiation released when the universe first became transparent. The result is something remarkable. The entire observable universe is immersed in a vast ocean of primordial light. The word ocean is useful because it helps illustrate just how completely this radiation fills space. Imagine a fish living deep within the sea. The fish is surrounded by water in every direction. No matter where it swims, the ocean remains present. The fish may rarely think about the water because it is such a constant part of its environment. Humanity exists in a somewhat similar situation. We live inside a cosmic ocean created more than 13 billion years ago. The difference is that this ocean is not made of water. It is made of ancient photons that have been traveling through the expanding universe since the earliest observable era of cosmic history. The existence of this radiation reveals something extraordinary about the Big Bang. Many people mistakenly imagine the Big Bang as a giant explosion that happened at a specific location in space. In that picture, one might expect the ancient radiation to be concentrated around some distant center. But the Big Bang was not an explosion within space. It was the rapid expansion of space itself. Because of this, the ancient light was released throughout the entire young universe, rather than from a single point. That is why the cosmic microwave background appears in every direction we observe. No matter where astronomers point their instruments, they encounter the same ancient glow. It surrounds Earth, the solar system, the Milky Way, and every galaxy throughout the observable cosmos. The universe is still filled with the afterglow of its own birth. What makes this even more fascinating is that the radiation appears remarkably uniform. When scientists first measured the cosmic microwave background, they discovered that its temperature is nearly identical across the entire sky. Wherever they looked, they found radiation with a temperature of about 2.7 degrees above absolute zero. This is astonishing because the regions producing this radiation are separated by enormous distances. Some lie billions of light years apart. Yet despite these immense separations, the ancient glow appears almost perfectly consistent. This uniformity became one of the greatest puzzles in cosmology. How could distant regions of the universe share such similar properties? Why did the ancient radiation appear so evenly distributed? These questions eventually help scientists develop new theories about the earliest moments of cosmic history, leading to deeper insights into how the universe evolved. Although the cosmic microwave background appears smooth on large scales, it is not completely uniform. Tiny variations exist throughout the radiation. These differences are incredibly small, often only a few millionths of a degree, yet they are among the most important patterns ever discovered. To understand why, imagine looking at the surface of a calm lake. From a distance, the water appears smooth and featureless. Upon closer inspection, however, tiny ripples become visible. Those ripples reveal information about winds, currents, and disturbances that would otherwise remain hidden. The tiny variations within the cosmic microwave background serve a similar purpose. They reveal subtle differences in the density of matter that existed in the infant universe. Some regions contained slightly more matter than others. These small irregularities later became the seeds from which galaxies, stars, and planets eventually formed. Without those tiny variations, the universe might look very different today. Galaxies may never have formed. Stars may never have ignited. Planets may never have emerged. The structures filling the cosmos today can trace their origins back to faint patterns hidden within this ancient radiation. This means the cosmic microwave background is much more than a relic of the past. It is a bridge connecting the earliest observable universe to everything that exists today. Every galaxy visible through a telescope, every star shining in the night sky, and every planet orbiting a distant sun ultimately emerged from conditions preserved within this primordial glow. Another remarkable aspect of this cosmic ocean is how difficult it remained to detect. The radiation is extremely weak. By the time it reaches us, its wavelengths have stretched into the microwave region of the electromagnetic spectrum. Human eyes cannot perceive these wavelengths. For most of history, people had no idea that such a signal existed, yet it surrounded them continuously. Entire civilizations rose and fell beneath a sky filled with ancient radiation without ever knowing it was there. Only in the 20th century did technology become advanced enough to reveal this hidden ocean. Sensitive radio instruments allowed scientists to detect the faint signal and confirm one of the most important predictions of modern cosmology. The discovery transformed our understanding of the universe. Suddenly, astronomers possessed direct evidence connecting the modern cosmos to its earliest observable state. The Big Bang was no longer merely a theoretical idea supported by indirect observations. Its ancient afterglow could actually be measured. The existence of this radiation also changes how we think about distance and time. When we look at a distant galaxy, we see light that has traveled across space for millions or billions of years. But the cosmic microwave background is even older. It comes from a time before galaxies existed at all. Every direction in the sky becomes a window into the distant past. The ancient radiation effectively surrounds us with a spherical image of the infant universe. Wherever we look, we encounter photons that have carried information across more than 13 billion years of cosmic history. Few discoveries reveal the scale of time as dramatically as this. The photons reaching Earth today began their journey long before the Sun existed. They traveled through space before the Milky Way acquired its current form. They crossed the cosmos before Earth formed, before life emerged, and before human beings appeared. Yet after all that time, they are still here, still moving, still carrying their ancient message. The most profound lesson is that the universe never completely forgets its past. Events that occurred near the beginning of cosmic history have left traces that remain visible today. The cosmic microwave background is one of the clearest examples of this cosmic memory. It is a faint but persistent reminder that the early universe has never entirely disappeared. It continues surrounding everything. Every galaxy drifts through this ancient ocean. Every star shines within it. Every planet orbits inside it. And every living thing exists within a universe still filled with the oldest light in existence. The invisible ocean of ancient radiation is not merely a scientific curiosity. It is one of the deepest connections between the present universe and its earliest moments. It surrounds us at every instant, carrying a record of a time when the cosmos was young and simple. More than 13 billion years later, that primordial glow continues flowing through space, reminding us that the story of the universe did not begin in darkness. It began in light. Some of the greatest scientific discoveries in history were not made by people searching for them. Instead, they appeared unexpectedly while researchers were focused on entirely different goals. Penicillin was discovered after an accidental observation in a laboratory. X-rays were uncovered while scientists were investigating electrical phenomena. Even the discovery of cosmic microwave background radiation, the oldest light in the universe, began with a mystery that seemed more like a technical problem than a revolutionary breakthrough. In the early 1960s, astronomy was undergoing a period of rapid advancement. New radio telescopes were allowing scientists to detect signals from space that were invisible to ordinary optical telescopes. Researchers were beginning to explore the universe through radio waves, uncovering phenomena that had remained hidden for centuries. A debate was taking place among cosmologists. Two competing ideas attempted to explain the origin of the universe. One was the Big Bang theory, which proposed that the universe began in a hot, dense state and expanded over time. The other was the steady-state theory, which suggested that the universe had always existed in roughly the same form and had no true beginning. Both models could explain certain observations, and for many years the scientific community remained divided. The question of which theory was correct remained one of the biggest mysteries in modern science. What few people realized was that the answer was already surrounding Earth. The ancient radiation left behind by the early universe was passing through space in every direction. It filled the cosmos with a faint microwave glow. Yet no one had detected it directly. The signal was extraordinarily weak. It could not be seen with ordinary telescopes. It produced no visible image in the sky, and because it arrived from every direction almost equally, it was easy to mistake for background noise. This is where the story takes an unexpected turn. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Laboratories in New Jersey. They were using a large horn-shaped radio antenna originally built for satellite communications. Their goal was not to study the birth of the universe. They were simply trying to make extremely precise radio measurements. As they worked with the antenna, they encountered a frustrating problem. A persistent background signal appeared in their data. No matter where they pointed the instrument, the signal remained. It came from every direction in the sky. Day or night, summer or winter, the mysterious noise refused to disappear. They assumed something was wrong with their equipment. Scientists are trained to be skeptical of unexpected results. Most unusual observations turn out to be measurement errors, instrument malfunctions, or environmental interference. Penzias and Wilson therefore began a careful investigation to locate the source of the unwanted signal. They checked the electronics. They tested the receivers. They examined nearby radio transmitters. They searched for possible sources of interference from cities, aircraft, and communication systems. Everything appeared normal, yet the signal remained. The mystery became increasingly frustrating because it seemed impossible to eliminate. Then they noticed another potential problem. Birds had been nesting inside the antenna. Specifically, pigeons had found their way into the large structure and left behind what the scientists politely described as white dielectric material, pigeon droppings. Concerned that the birds might somehow be contaminating their measurements, the researchers cleaned the antenna thoroughly and removed the pigeons. After all this effort, they repeated their observations. The mysterious signal was still there. It became clear that something far more interesting might be happening. Unknown to Penzias and Wilson, another group of scientists at nearby Princeton University was working on a very different problem. Researchers there were searching for the faint radiation that should remain from the early universe if the Big Bang theory was correct. Years earlier, physicists such as George Gamow, Ralph Alpha, and Robert Herman had predicted that a hot early universe should leave behind a faint glow of radiation. As the universe expanded, that radiation would cool and stretch into microwave wavelengths. If detected, it would provide powerful evidence that the universe had once existed in a much hotter and denser state. The prediction was remarkable. The problem was that no one had yet observed the signal. When the two groups learned about each other's work, the pieces suddenly fell into place. The persistent background noise detected by Penzias and Wilson was not a technical problem. It was the ancient afterglow of the Big Bang itself. The unwanted signal was the cosmic microwave background. For more than 13 billion years, these photons had traveled through the expanding universe. They crossed immense distances, survived the formation of galaxies and stars, and eventually reached Earth, where they appeared as a faint hiss inside a radio antenna. What had begun as a frustrating engineering problem instantly became one of the most important discoveries in the history of science. The implications were enormous. Astronomers possessed direct observational evidence that the universe had evolved from a hot, dense early state. The discovery strongly supported the Big Bang model and dealt a devastating blow to the steady-state theory. Cosmology changed almost overnight. Before the discovery, the Big Bang was one of several competing explanations for the universe. After the discovery, it became the leading framework for understanding cosmic origins. Scientists suddenly had access to a signal originating from one of the earliest observable periods in cosmic history. The cosmic microwave background became a new scientific tool. Researchers realized that this ancient radiation contained valuable information about the young universe. Its temperature, distribution, and subtle variations could reveal details about conditions that existed hundreds of thousands of years after the Big Bang. The universe had preserved a photograph of its infancy, and humanity had finally found it. The years that followed brought even more remarkable discoveries. Satellites such as COBE, WMAP, and Planck mapped the radiation with increasing precision. Tiny fluctuations hidden within the ancient glow revealed the seeds of future galaxies and helped scientists measure the age, composition, and evolution of the universe with extraordinary accuracy. What began as unexplained noise evolved into one of the greatest sources of knowledge in modern astronomy. The most remarkable aspect of the story is how ordinary it seemed at the beginning. There was no dramatic announcement, no sudden flash of light, no unmistakable sign that a revolutionary discovery was waiting. There was only a stubborn signal that refused to disappear. Yet hidden within that faint background noise was a message from the dawn of time. The discovery reminds us that the universe often reveals its deepest secrets in unexpected ways. Sometimes the greatest breakthroughs are not found by looking exactly where we expect. Sometimes they appear as anomalies, puzzles, or problems that refuse to go away. Of the cosmic microwave background, a mysterious hiss inside a radio antenna became humanity's first direct glimpse of the infant universe. It transformed cosmology from a field dominated by speculation into one grounded by powerful observational evidence. More than half a century later, that accidental discovery remains one of the most important moments in scientific history. The ancient radiation is still arriving from every direction in the sky, carrying information across billions of years. And it all came to humanity's attention because two scientists refused to ignore a signal that seemed out of place. What they discovered was not merely noise, it was the oldest light in existence, still whispering the story of the universe's beginning. Photographs have a remarkable ability to preserve moments that would otherwise disappear forever. A single image can capture a birthday celebration, a historic event, or a fleeting moment in someone's life, and preserve it long after the moment itself has passed. Years later, people can look at the photograph and see a scene exactly as it existed at a particular point in time. The cosmic microwave background serves a similar purpose for the universe. It is often described as the oldest photograph in existence, not because it was taken with a camera, but because it preserves a record of the cosmos at a specific moment in its early history. When scientists study this ancient light, they are looking at a snapshot of the universe as it appeared roughly 380,000 years after the Big Bang. To appreciate how extraordinary this is, consider the age of the universe today. Modern measurements indicate that the cosmos is approximately 13.8 billion years old. Compared to that immense time span, 380,000 years is almost the beginning. If the entire history of the universe were compressed into a single calendar year, the moment captured by the cosmic microwave background would occur within the first few minutes of January 1st. Everything familiar came later. Stars had not yet formed. Galaxies did not yet exist. Planets, moons, oceans, and life were still far in the future. The universe was young, simple, and remarkably different from the cosmos we see today. Yet somehow, a record of that ancient era survived. The reason lies in the moment when the universe became transparent. Before transparency, photons were trapped inside a dense plasma of charged particles. They collided constantly with free electrons, changing direction countless times. Any information carried by the light was continuously scrambled. Looking into this period with ordinary light would be like trying to see through a wall of dense fog. Then the universe cooled enough for stable atoms to form. As electrons combined with atomic nuclei, the cosmic fog suddenly cleared. Photons were released and began traveling freely across space. Those photons carried information about the exact conditions that existed at the moment of their release. The universe created a snapshot of itself. Every photon became part of a vast cosmic record, preserving the state of the infant cosmos at that precise time. Imagine taking a photograph of a city before any buildings have been constructed. The image would not show skyscrapers, highways, or neighborhoods. Instead, it would reveal the landscape from which the city would eventually emerge. The cosmic microwave background serves a similar role. It shows the universe before stars and galaxies formed, capturing the raw conditions that later gave rise to everything we see today. This makes the ancient light far more than a simple glow filling space. It is information. Encoded within the radiation are details about temperature, density, motion, and the distribution of matter throughout the young universe. Every region of the sky contains pieces of this information, allowing scientists to reconstruct what the cosmos looked like during its earliest observable stage. What makes this possible is the extraordinary journey of the photons themselves. After their release, they traveled across the expanding universe for more than 13 billion years. During that time, galaxies formed, stars ignited, planets emerged, and cosmic structures evolved on enormous scales. Yet the photons continued moving through space, preserving a memory of their origin. Unlike physical objects, which can be altered by collisions, erosion, or other processes, these photons largely retained the information they carried from the moment they were released. Although their wavelengths stretched as the universe expanded, the underlying patterns embedded within the radiation remained. As a result, the cosmic microwave background functions like a time capsule. A time capsule is designed to preserve information from one era so that future generations can study it later. The ancient light performs the same role on a cosmic scale. It carries information from an era that no longer exists, delivering that information billions of years into the future. When scientists analyze the cosmic microwave background, they are effectively opening a time capsule created near the dawn of cosmic history. The details preserved within this radiation are astonishingly precise. Measurements reveal that the early universe was remarkably uniform. Temperatures across vast regions of space differed by only tiny amounts. On average, the cosmos looked almost the same in every direction. This might seem unimportant. It tells us something profound. The remarkable uniformity suggests that the early universe underwent processes that distributed energy and matter with extraordinary consistency. Understanding how this happened has become one of the central goals of modern cosmology. The snapshot reveals something equally important. The infant universe was not perfectly uniform. Tiny fluctuations existed within the radiation. Some regions were slightly denser than others, some were slightly warmer or cooler. These differences were incredibly small, often less than 1 part in 100,000. But they would eventually shape the future of the cosmos. Those tiny variations acted as seeds. Gravity gradually amplified them over millions and billions of years. Regions containing slightly more matter attracted additional material. As the process continued, larger structures began forming. Clouds of gas collapsed. The first stars ignited. Galaxies emerged. Clusters of galaxies assembled. Over vast stretches of time, the complex universe we inhabit today grew from those tiny imperfections preserved in the cosmic microwave background. This means the snapshot contains more than a picture of the past. It contains clues about the future. By studying the patterns embedded within the ancient light, scientists can understand how the modern universe developed from its earliest beginnings. The radiation provides a direct connection between the infant cosmos and the enormous structures visible today. Every galaxy can trace part of its history back to patterns recorded in this ancient photograph. So can every star, every planet, every atom within our bodies. The structures that eventually allowed life to emerge were influenced by conditions preserved in the cosmic microwave background billions of years ago. Another remarkable aspect of this cosmic snapshot is that it allows scientists to test theories about the universe with extraordinary precision. Cosmological models make specific predictions about what the early universe should look like. By comparing those predictions with observations of the cosmic microwave background, researchers can determine which ideas accurately describe reality. The agreement between theory and observation has been one of the greatest successes in modern science. The ancient light has helped scientists estimate the age of the universe, measure its composition, determine its geometry, and better understand its evolution across cosmic time. Few scientific observations have provided so much information about such a distant era. What makes this achievement even more remarkable is that humanity discovered the snapshot accidentally. The photons carrying this ancient record had been passing through space for billions of years before anyone realized they existed. Entire civilizations lived and disappeared beneath a sky filled with primordial radiation without knowing that the universe's earliest photograph surrounded them. Today, sensitive instruments allow us to study that photograph in extraordinary detail. Space missions have mapped the cosmic microwave background across the entire sky, revealing structures and patterns invisible to the human eye. These maps have become some of the most important images in the history of astronomy because they show the universe at a stage no telescope can observe directly through any other means. The most beautiful aspect of this story is what it reveals about the cosmos itself. The universe has preserved a memory of its infancy. Despite billions of years of change, expansion, and evolution, a record of one of its earliest moments still exists. The ancient light continues traveling through space, carrying information from a time before stars illuminated the heavens. Every photon is part of a message from the distant past. Together they form a snapshot of a universe that was young, simple, and full of potential. By studying that snapshot, humanity has gained one of its deepest insights into the origin of cosmic structure and the history of existence itself. The cosmic microwave background is therefore much more than ancient radiation. It is a preserved image of the infant universe, a cosmic photograph taken near the beginning of time and delivered across billions of years to those capable of understanding what it contains. And within that remarkable image lies the story of how the universe we know today first began to take shape. The cosmic microwave background appears almost perfectly uniform. When scientists first detected this ancient radiation, it seemed to come from every direction with nearly the same temperature. The signal looked smooth, consistent, and remarkably featureless. If the early universe had truly been this uniform, it would have raised a fascinating but troubling question. How did such a smooth universe eventually produce galaxies, stars, planets, and everything else we see today? After all, structure cannot emerge from perfect uniformity. If matter were distributed exactly the same everywhere, gravity would have no preferred locations to gather material. The cosmos would remain largely smooth and featureless even after billions of years of evolution. Yet the universe is anything but featureless. Galaxies fill space. Clusters of galaxies stretch across hundreds of millions of light years. Stars populate those galaxies. Planets orbit those stars. Somewhere among those planets, life emerged, Clearly, something in the early universe provided the starting point for all of this complexity. The answer was hidden within the cosmic microwave background itself. As technology improved, astronomers began measuring the ancient radiation with extraordinary precision. Instead of examining only its average temperature, they searched for tiny variations hidden within the signal. What they discovered transformed cosmology. The early universe was not perfectly smooth. It contained minute patterns spread across the sky. These patterns were astonishingly small. In many regions, temperature differences amounted to only a few millionths of a degree. To appreciate how tiny this is, imagine measuring the temperature of a large ocean and discovering differences so small that they are almost impossible to detect. Yet, despite their subtle nature, these variations would eventually shape the entire history of the cosmos. Scientists often refer to these slight differences as fluctuations or anisotropies. Although the names sound technical, the idea is simple. Some regions of the young universe contained slightly more matter than average. Other regions contained slightly less. The differences were incredibly small, but they mattered enormously. Imagine a perfectly flat landscape covered with a thin layer of rainwater. If one part of the ground is even slightly lower than the surrounding area, water gradually begins flowing toward that depression. Over time, more water accumulates there, making the low region deeper and attracting even more water. Gravity works in a similar way. Regions containing slightly more matter possess slightly stronger gravitational pull. Over millions of years, these denser regions attract additional material. As more matter gathers, gravity becomes stronger, accelerating the process. What begins as a tiny difference eventually becomes a major structure. This is exactly what happened in the universe. The faint patterns hidden within the cosmic microwave background became the seeds from which all cosmic structure grew. The denser regions gradually evolved into enormous clouds of gas. Those clouds collapsed to form the first stars. Groups of stars assembled into galaxies. Galaxies gathered into clusters. Clusters connected through immense filaments stretching across the cosmos. Every visible structure in the modern universe traces its ancestry back to these tiny fluctuations. Without them, the night sky would look dramatically different. There might be no galaxies, no stars, no planets, possibly no life. The entire cosmic story depended on subtle irregularities hidden within the universe's first glow. What makes these patterns even more remarkable is that they reveal conditions from an era long before any stars existed. The fluctuations were already present when the universe was only about 380,000 years old. At that time, galaxies had not formed, yet the blueprint for future galaxies was already encoded within the radiation. It is almost as if the universe carried an architectural plan for its future development. The structures had not been built yet, but the instructions were already present. When scientists create detailed maps of the cosmic microwave background, they often use colors to represent tiny temperature differences. Regions that are slightly warmer appear in one color, while slightly cooler regions appear in another. These maps reveal a fascinating pattern. Rather than being completely random, the fluctuations follow statistical relationships that provide important clues about the earliest moments of cosmic history. By studying these patterns, cosmologists can investigate events that occurred far earlier than the release of the cosmic microwave background itself. This is possible because the fluctuations did not suddenly appear when the universe became transparent. Their origins reach back to an even earlier period. Many scientists believe the seeds of these patterns were created during a brief episode known as cosmic inflation. According to this idea, the universe underwent an extraordinary rapid expansion during its earliest fraction of a second. Tiny quantum fluctuations present at microscopic scales were stretched across enormous distances. What began as minute variations in the infant universe eventually became the fluctuations visible in the cosmic microwave background. Billions of years later, those same fluctuations evolved into galaxies and clusters of galaxies. This connection between the smallest and largest scales in existence is one of the most remarkable discoveries in modern science. Quantum processes occurring in the earliest moments of cosmic history may have influenced the distribution of galaxies across billions of light-years. The tiny patterns hidden within the ancient light therefore provide evidence not only about the universe 380,000 years after the Big Bang, but also about events occurring much earlier. This makes the cosmic microwave background an extraordinary scientific tool. Astronomers are not simply looking at ancient radiation, they are examining a record containing clues about the origin of cosmic structure, the behavior of matter and energy, and the processes that shaped the universe during its infancy. Few sources of information offer such a direct connection to the distant past. The precision of modern measurements is astonishing. Space missions such as COBE first detected the fluctuations hidden within the radiation. Later missions including WMAP and Planck mapped these patterns with far greater detail. The resulting images became some of the most important scientific maps ever created. Every spot on those maps contains information about conditions that existed near the dawn of cosmic history. Researchers have used this information to estimate the age of the universe, measure its composition, determine its geometry, and refine models describing its evolution. In many respects, the tiny patterns hidden within the cosmic microwave background have become one of the foundations of modern cosmology. They demonstrate that the early universe was neither perfectly smooth nor completely chaotic. It contained just enough variation to allow complexity to emerge. This balance proved essential. Too much variation might have caused matter to collapse rapidly into enormous structures. Too little variation could have left the universe largely featureless. The fluctuations appear to have possessed exactly the right characteristics to produce the rich cosmic landscape observed today. That fact alone is extraordinary. Every galaxy visible through a telescope, every star illuminates the night sky, every planet orbiting distant suns, and every living being capable of wandering about the universe, all of these can trace part of their history back to tiny temperature differences hidden within the first light of the cosmos. The ancient glow may appear smooth when viewed from afar, but hidden within it is a delicate pattern that shaped everything that followed. The cosmic microwave background is therefore much more than the oldest light in existence. It is a cosmic blueprint, preserving the faint fingerprints of processes that transformed a young, nearly uniform universe into the vast and complex cosmos we inhabit today. By studying those tiny patterns, scientists are not merely observing ancient radiation, they are uncovering the earliest hints of every galaxy, every star, and every world that would eventually emerge from the darkness of the infant universe. When we look into the night sky, galaxies appear as some of the largest and most magnificent structures in existence. The Milky Way alone contains hundreds of billions of stars. Beyond it lie countless other galaxies, each with their own stars, planets, nebulae, and black holes. Some galaxies are graceful spirals stretching across vast distances. Others are enormous elliptical systems containing trillions of stars. Together they form the visible architecture of the universe. Yet one of the greatest mysteries in astronomy has always been this: how did galaxies begin? They were not present in the earliest observable universe. When the cosmic microwave background was released about 380,000 years after the Big Bang, the cosmos contained no galaxies, no stars, and no planets. The universe was still a relatively simple place filled mostly with hydrogen, helium, radiation, and invisible dark matter. And yet somehow, from that simple beginning, emerged the vast cosmic structures we observe today. The answer lies hidden within the ancient signal itself. The cosmic microwave background is far more than a relic of the Big Bang. It is a record of the conditions that existed before galaxies were born. By studying the subtle patterns preserved within this radiation, scientists can investigate the earliest stages of a process that eventually transformed a nearly uniform universe into one filled with billions of galaxies. To understand this transformation, imagine looking at a freshly planted field immediately after seeds have been scattered across the soil. At first, the field appears mostly empty. There are no visible plants, no flowers, and no trees. Yet hidden beneath the surface are the seeds that will eventually shape the landscape. The early universe was similar. When the cosmic microwave background was released, galaxies did not yet exist. However, the seeds of future galaxies were already present. These seeds appeared as tiny fluctuations in density. Some regions of the universe contained slightly more matter than average, while others contained slightly less. The differences were incredibly small, often only fractions of a percent. Yet those tiny variations became the foundation upon which all large-scale cosmic structure would later grow. Gravity was the key. Wherever a region contained slightly more matter, its gravitational pull became slightly stronger. That stronger gravity attracted additional matter from nearby regions. As more material gathered, the gravitational pull increased further, attracting even more matter. This process continued for millions of years. Small differences gradually became larger ones. Tiny irregularities slowly evolved into enormous concentrations of matter. The universe was effectively amplifying its own imperfections. One useful comparison is a snowball rolling down a hill. At the beginning, the snowball may be small and insignificant. As it rolls, however, it collects additional snow. The larger it becomes, the more snow it can gather. Growth accelerates over time. Gravity operates in a similar way. Regions that began slightly denser than average gradually attracted more material, becoming increasingly massive. Over vast stretches of time, these growing structures laid the foundation for future galaxies. An important part of this story involves dark matter. Although dark matter remains invisible and cannot be observed directly, scientists believe it played a critical role in the formation of galaxies. Long before ordinary matter began collapsing into stars and galaxies, dark matter was already creating gravitational structures throughout the young universe. The fluctuations visible in the cosmic microwave background provide indirect evidence of these early processes. Researchers believe dark matter formed enormous gravitational frameworks, often called halos, that acted like scaffolding for future galaxies. Ordinary matter then fell into these invisible structures, where gas accumulated and eventually collapsed under gravity. Without this hidden framework, galaxy formation would have been far more difficult. The ancient signal therefore provides clues not only about visible matter, but also about the invisible components that helped shape the universe. As time passed, the densest regions continued growing. Millions of years after the release of the cosmic microwave background, large clouds of hydrogen and helium began collapsing. Temperatures and pressures increased within these clouds until the first stars ignited. This moment transformed the cosmos. For hundreds of millions of years, the universe had existed without stars. Then, gradually, the first points of starlight appeared. These stars gathered into larger groups. The groups merged and evolved, eventually forming the earliest galaxies. The process was neither quick nor simple. Galaxies did not emerge fully formed. They grew through repeated mergers, interactions, and continuous accumulation of matter. Small structures combined into larger ones. Young galaxies collided and merged, creating increasingly complex systems. Over billions of years, this process produced the enormous variety of galaxies observed today. Some became elegant spiral galaxies like the Milky Way. Others evolved into giant elliptical systems. Still others formed irregular shapes due to repeated interactions and collisions. Remarkably, the origins of all these structures can be traced back to the tiny fluctuations preserved within the cosmic microwave background. This is one of the most powerful achievements of modern cosmology. Scientists can compare detailed maps of the ancient radiation with computer simulations of cosmic evolution. Starting with the tiny density variations observed in the cosmic microwave background, the simulations reproduce many of the structures seen in the modern universe. The match was extraordinary. Galaxies, galaxy clusters, and even the vast cosmic web connecting them emerged naturally from the same initial conditions preserved in the ancient light. It is almost like discovering the blueprint for a massive city and then finding that the finished city matches the blueprint with remarkable accuracy. The cosmic microwave background serves as that blueprint. It reveals the starting conditions from which cosmic structure developed. The significance of this discovery cannot be overstated. Before the detection of the cosmic microwave background, scientists had theories about how galaxies might form, but they lacked direct evidence of the universe before galaxies existed. The ancient radiation changed that. Researchers could observe the universe during a stage when the seeds of galaxies were present, but the galaxies themselves had not yet formed. This provided a missing chapter in cosmic history. Seeing only the finished result, scientists could now study the beginning of the process. The ancient signal also reveals something profound about the nature of the universe. The galaxies we see today were not randomly distributed across space. Their origins can be traced to patterns that existed when the universe was still incredibly young. In other words, the large-scale structure of the modern cosmos was influenced by conditions established billions of years before the first galaxy ever appeared. The universe carried the instructions for its future within its earliest moments. Every spiral galaxy, every giant cluster, every supercluster stretches across hundreds of millions of light-years, all emerged from tiny variations hidden within the first observable light. This realization transforms the way we view the night sky. When we look at a galaxy through a telescope, we are not simply observing an isolated collection of stars. We are witnessing the outcome of a process that began near the dawn of cosmic history. The galaxy's existence can be traced back through billions of years of evolution to subtle patterns preserved in the cosmic microwave background. Every galaxy contains a memory of the infant universe. Its stars, gas clouds, and planets all owe their existence to tiny fluctuations that appeared long before galaxies themselves were born. The most beautiful lesson is that complexity emerged from simplicity. The early universe was remarkably smooth, yet hidden within that smoothness were small imperfections. Gravity amplified those imperfections over billions of years, transforming them into the vast structures that now fill the cosmos. The ancient signal preserves the moment when those seeds first became visible. It shows us a universe before galaxies existed, while simultaneously revealing how galaxies would eventually come into being. That is why the cosmic microwave background remains one of the most important discoveries in the history of astronomy. It allows humanity to look beyond the galaxies of today and glimpse the conditions that made those galaxies possible. It provides a direct connection between the infant universe and the magnificent cosmic structures that now illuminate the heavens. Every galaxy in the night sky is part of a story that began with tiny patterns hidden within the universe's first glow. And by studying that ancient signal, we continue uncovering how the cosmos transformed from a nearly uniform sea of particles into a universe filled with stars, galaxies, and worlds beyond imagination. Throughout history, humanity has searched for clues about its origins. Archaeologists study ancient ruins to understand lost civilizations. Geologists examine layers of rock to reconstruct Earth's distant past. Historians analyze documents and artifacts to uncover events that occurred centuries ago. In every case, understanding the present requires evidence from the past. Cosmology faces the same challenge, but on a far greater scale. Scientists are not trying to reconstruct the history of a city, a continent, or even a planet. They are trying to understand the history of the entire universe. The difficulty is obvious. The events that shaped the cosmos occurred billions of years ago, long before stars, planets, or life existed. Most traces of those ancient eras have disappeared or transformed beyond recognition. Yet one extraordinary piece of evidence survived: the cosmic microwave background. This ancient radiation is often called the ghost of the Big Bang because it is a lingering remnant of the universe's earliest observable chapter. More than 13 billion years after its release, it continues traveling through space, carrying information from a time when the cosmos was only a tiny fraction of its current age. What makes this signal so important is not merely its age, it is the amount of information it contains. Imagine finding a single page from a lost book. The page might reveal something about the story, but much of the larger narrative would remain hidden. Now imagine finding an entire chapter preserved almost perfectly. Suddenly, the story becomes far easier to understand. The cosmic microwave background is like an entire chapter preserved from the earliest history of the universe. Before its discovery, many ideas about the origin of the cosmos remain difficult to test. Scientists could propose theories, but they lacked direct observational evidence from the universe's infancy. The ancient radiation changed that situation completely. Researchers possessed a signal that came directly from the young universe itself. It was not an interpretation. It was not a simulation. It was not an indirect consequence of later events. It was actual radiation released when the cosmos was only about 380,000 years old. That fact alone makes it one of the most valuable scientific discoveries ever made. The importance of the cosmic microwave background begins with its confirmation of the Big Bang model. Before its detection, competing explanations for the universe still existed. Some scientists favored the steady-state theory, which proposed that the universe had always existed in roughly the same form. Others supported the idea of a hot, dense beginning. The discovery of the ancient radiation provided powerful evidence that the universe truly evolved from a much hotter and denser state. It was exactly the type of signal the Big Bang model predicted. Finding it transformed cosmology from a field filled with competing possibilities into one grounded by direct observational evidence. But the cosmic microwave background does much more than support the Big Bang. It allows scientists to measure fundamental properties of the universe with extraordinary precision. By studying the temperature and distribution of the radiation, researchers have estimated the age of the universe to be approximately 13.8 billion years. They have measured its overall geometry, investigated its composition, and determined how matter and energy are distributed across cosmic scales. Few scientific observations have provided such a wide range of information. The ancient light has become one of the most powerful tools ever used to study the cosmos. Another reason this signal remains so important is that it provides a direct connection to a time that cannot be observed in any other way. Most astronomical observations involve stars, galaxies, planets, or other structures that formed long after the universe's beginning. These objects reveal important information, but they do not show the cosmos during its earliest observable stage. The cosmic microwave background does. It acts like a window into a period before galaxies existed, a period before stars illuminated the darkness, a period when the universe was still simple enough for scientists to study its basic ingredients directly. Without this ancient radiation, much of that chapter of cosmic history would remain hidden. The signal has also become one of the strongest sources of evidence for cosmic inflation. Inflation is the idea that the universe experienced an incredibly rapid expansion during its earliest fraction of a second. According to this theory, microscopic quantum fluctuations were stretched across enormous distances, eventually becoming the seeds of galaxies and large-scale cosmic structure. The tiny patterns preserved within the cosmic microwave background match many predictions made by inflationary models. Although questions remain, the ancient radiation provides some of the strongest observational support for the idea that inflation occurred. This means the signal does not merely tell us about conditions 380,000 years after the Big Bang. It may also contain clues about events that happened far earlier. The cosmic microwave background functions like a cosmic fossil. Fossils preserve traces of life that existed millions of years ago. They allow scientists to study creatures that vanished long before humans appeared. The ancient radiation serves a similar purpose for cosmology. It preserves traces of physical conditions that existed near the beginning of time itself. By examining those traces, researchers can reconstruct events that would otherwise be lost forever. The cosmic microwave background has also revealed how remarkably balanced the universe appears to be. The early cosmos was neither perfectly smooth nor wildly chaotic. It contained just enough variation to allow galaxies and stars to form, while remaining stable enough for large-scale order to emerge. This balance continues to fascinate scientists because small changes in the initial conditions could have produced a dramatically different universe. If the fluctuations had been much larger, matter might have collapsed too rapidly into dense structures. If they had been much smaller, galaxies might never have formed at all. The ancient signal reveals a cosmos that possessed exactly the right conditions for complexity to emerge. Another remarkable aspect of the cosmic microwave background is its universality. Every observer in the universe would encounter it, whether one stands on Earth, on a distant planet orbiting another star, or within a remote galaxy billions of light years away. The ancient radiation remains present. It is one of the few truly universal features of the cosmos. Every civilization capable of building sensitive instruments would eventually discover it. Every advanced observer would encounter the same ancient glow and learn that the universe carries a memory of its earliest observable moments. This makes the signal something more than a scientific measurement. It is a shared cosmic heritage, a message written into the fabric of the universe itself. Even today, researchers continue finding new ways to study the cosmic microwave background. More sensitive instruments reveal finer details within the radiation. Improved observations help refine cosmological models. Future missions may uncover subtle signals that provide clues about dark matter, dark energy, or the earliest moments of inflation. The ancient light still has secrets left to reveal. That is one reason it remains so important. Most scientific discoveries answer a question and then become part of established knowledge. The cosmic microwave background continues doing both. It answers old questions while simultaneously generating new ones. Every improvement in observational precision reveals additional layers of information hidden within the radiation. The signal remains one of the richest sources of knowledge available to modern science. Most profound lesson is that the universe remembers. The events that occurred near the beginning of cosmic history have not completely vanished. Their traces remain embedded within the ancient light that still fills space today. The ghost of the Big Bang is therefore more than radiation. It is evidence. It is a record. It is a messenger from the distant past. For more than 13 billion years, it has traveled across the cosmos carrying information about a universe that no longer exists. It has survived the formation of galaxies, the birth of stars, the emergence of planets, and the evolution of life. Through all of those transformations, the ancient signal endured. Today, it continues whispering the story of the universe's beginning. Every faint microwave photon crossing space is part of that story. Together, they form one of the greatest clues in science, a clue that allows humanity to look farther into the past than any other source of light and uncover the earliest observable chapter of existence itself. The ghost of the Big Bang remains one of the greatest clues in science because it bridges the gap between the present universe and its ancient origins. It reminds us that the cosmos has a memory, that its earliest moments left traces that still survive, and that even after billions of years, the story of the beginning has never completely faded away. The ghost of the Big Bang is not a distant object hidden somewhere in space. It is a cosmic message that has been traveling across the universe for more than 13 billion years. Long before stars illuminated the heavens and galaxies filled the cosmos, this ancient light began its journey. Today, it continues to surround us, carrying a record of the universe's earliest chapter. Every faint signal is a reminder that the cosmos has a memory and that its beginning has never completely faded away. As long as this primordial light continues its endless voyage, the story of the Big Bang remains written across the sky, waiting for those who choose to look deeper into the origins of existence itself.